welcome to the Ocean Graduate School seminar, everyone. It's the Thursday before a long weekend, so I'm hosting my own seminar, but thanks everyone for dialing in. So those who don't know me, my name's Matt Rayson. I'm a research fellow here in the Ocean Graduate School. And as you can guess from my title, my research is on ocean physics. So today I'm going to talk about, give a general overview of ocean current variability at horizontal scales of 1 to 100 kilometres. And the reason I'm giving this talk is the processes of these scales tie into some of the research projects that we're currently working on, both within our group in the Ocean Graduate School and some other collaborations that I'll talk about as we go on. So I've just listed a bunch of collaborators here and I won't go through all of them. So just to start with, I'll just give a 3-minute introduction to the evolution of physical oceanography and the evolution of our understanding. So this is sort of the traditional picture of ocean currents from a map from 1943. And basically, you have these streamlines of currents flow across the ocean basins. Some of these are correct, some of these lines are correct, some are not correct. So for example, fluent currents flowing northward in this plot. So, but that was the understanding at the time, that the ocean currents form these large 1,000+ kilometre wide streams that circulate across the ocean basins. And the other thing that was known, and it's probably been known thousands of years, is that tides are important, especially in coastal regions. And then moving on to the modern picture of oceanography. So this came about with the satellite era, so from the 70s and 80s onwards, when they started measuring sea surface height in particular. What started to become clear that the ocean is actually full of eddies, not these big streaming flows. So if you take a snapshot of the ocean, you'll see eddies. And this satellite, they resolved what are called mesoscale eddies, so length scales of 100 to 1,000 kilometres. And another way of stating that the ocean is full of eddies is that greater than 90% of the kinetic energy at these larger scales is actually in eddies, not in the large streams. Also, what is known, internal gravity waves exist, and it was speculated that they may be important for the large scale flow. Then moving on to now, which I'll term postmodern oceanography, although that's not a real term. And what's become evident since people started taking photos from space is that there's actually a lot finer scale processes. So on the left here is a photograph taken out the window of a space shuttle over the Sea of Japan. And what you see are these much finer scale eddies. So lengths here, scale bar down here is 12 kilometres. So these are less than 10 kilometres. Also in this photo, you can see these bands. So these are nonlinear internal gravity waves. And then on the right is another example, and this is taken from an orbiting satellite, so a modern satellite, and it's false color imagery over the Baltic Sea. And what you see at scales of 10 kilometres are these eddies, and then zooming in, you start down to scales of 1 kilometre, you start seeing all these finer filaments and fronts forming. So the postmodern view is that the ocean is also full of these submesoscale eddies, fronts and filaments. and internal gravity waves, which was known all along as well. And the other thing that's become apparent is that, and proven, is that the process of these finer scales influence the larger scale circulation. So predicting large scale circulation requires some treatment of these finer scale processes. So then what I'm going to talk about today is 4 topics. So firstly, it's going to give a general overview of these ocean processes at the 1 to 100 kilometre scales. Second, I'll give a general overview of surface current measurement techniques, and I'll differentiate between what is measured and what is inferred. That's not clear. Third, I'll talk about ocean models and their limitations for studying processes at these scales and show some pretty movies along the way. And then last, and we'll spend a bit of time on this, is talking about some of the current projects within our group and the efforts to measure or infer the surface currents at these length scales. So starting with the overview of the processes. So I've already alluded to this submesoscale eddies. So these are terms coined by oceanographers, mesoscale and submesoscale. The point of separation between them is actually defined dynamically. There's no clear length scale separating them. Rule of thumb, though, is that 100 kilometres is a pretty good cutoff. And so what I mean by dynamically defined is, if you think about mesoscale eddies, so the larger eddies, there's a horizontal momentum balance between 2 terms. So the Coriolis force and the horizontal pressure gradient, and that's called geostrophic balance. Submesoscale eddies are a lot more complicated, and the momentum balance is in between. The horizontal momentum balance is between more of the terms in the equation. So you now have these nonlinear advective terms, unsteady terms, and also it's becoming apparent that the turbulent shear stress processes have a leading order effect on the evolution of some of these finer scale eddies. So the other process that I alluded to at the start are internal gravity waves, and this can be broken down into internal tides and nonlinear internal waves. So starting with internal tides, so internal tides typically have frequencies of 1 to 2 cycles per day, so similar to the surface tides. They cause horizontal variations in surface currents of roughly 50 to 150 kilometres. So this is sort of the outer limit of the scales we're interested in. In terms of measurement of the internal gravity waves, they are detectable using the satellite altimetry record. So that's the sea surface height measurements. They cause a small perturbation in sea surface height. And that's what you can see on the right here. So this is from Zarin 2019, and it's showing the amplitude of the semi-diurnal perturbation to the sea surface height across the northern Pacific, I guess. And yeah, then zooming in, so this is from a student from our group, Yankin Gong, using the same data, but zooming in around the Indo-Australian and the Northwest Shelf. Yeah, you can see that now the finer details of these waves and how they evolve away from source regions. So yeah, this length between these peaks is about 50 to 100 kilometres. So, and then the last process is the nonlinear internal waves. So these are internal waves that have steepened and started dispersing into these higher frequency packets. So they have fluctuations of about 100 cycles per day, 10 to 60 minute period, that is. The length scales, so across the crest it's 1 to 2 kilometres, and along the crest is roughly 5 to some unknown distance. And these waves, we know that they're from moorings, but they're also detectable using sunglint imagery like I showed earlier and like is shown on the right here. So this is grayscale imagery from one of the bands from the Sentinel-2 satellite. And so what you see are these long crests, and this is changes in sunglint is what you're seeing here. But then zooming in down here, so this box down here is about 30 kilometres across, and you can see these packets are about 1 to 2 kilometres width, and this length scale is much larger. So everything I've shown you up to this point are not surface currents. These are observations of other traces, so sunglint, brightness, temperature, ocean colour. And so the question is, what do the surface currents actually look like? The problem is it's extremely difficult to measure the spatial variability of currents at these finer scales, and part of the reason for that is because at the finer scales, processes evolve on timescales of hours to days, so they evolve too quickly to drive a ship back and forward across them to measure well. So the solution really is to blend dynamical models with measurements of these other variables, so things like the sea surface height, surface waves, to then infer what the currents look like at these scales. So now I'll move into an overview of the measurement techniques, and I'll start with this question: are we measuring or are we inferring surface currents? And there's a bit of a spectrum here between what is measurement and what is modelled, I guess. So one method for measuring currents is tracking movement of water particles and calculating the displacement, dividing it by the time. And this is the general concept of how acoustic current meters work. Satellite track drifters also, you can estimate currents from that. It's very direct. And then getting less direct and down towards the inference end of the spectrum is measuring other ocean variables and using some relatively simple function to infer the velocity. And so this is how things like high frequency radar, which I'll talk about in a minute, they detect the Doppler shift of surface waves and then infer the currents from that. And the currents derived from the altimetry satellites, so the ones that measure sea surface height, use a simple model, so the geostrophic balance, to then infer what the currents are. And then going further down towards inference is measuring another ocean state variable and using a much more complicated function to infer the velocity. So, and this is an example would be these data assimilating nonlinear ocean models. So, oops. So I'll give an example what I mean by inferred currents. So I'll step you through how currents are derived from the the current altimetry records. So if you go to like IMOS Ocean Currents website, you'll see spatial fields of ocean current vectors that look like this. There's all sorts of eddies and streams and whatnot in this, but it's important to remember that these are actually inferred currents, not directly measured. And the way they do this is to fly a satellite over the Earth, and it measures the sea surface height along these tracks, allowing for corrections due to atmospheric effects, tides, etc. And so basically you get a measurement of a point along that track every 5 or so days, and the distance between these tracks is roughly 100 kilometres or more. The second step is that because it's these are sparse measurements in space and time, they then interpolate or model onto a continuous space-time grid, and they use this technique called optimal interpolation to do this. So that basically gives you these smooth maps of what this sea surface height looks like, noting that there are various assumptions that go into these spatial modelling tools, spatiotemporal modelling tools. And the fourth step, the last step, is using a simple dynamic model. So the geostrophic balance, which I talked about earlier, used for mesoscale eddies, is used to calculate the velocity from the measured sea surface height. So this is great data for resolving eddies at larger scales, but it only resolves scales greater than roughly 200 kilometres, so the mesoscale eddies. And another point that I'll make later as well is even if these satellites measured at finer resolution in space, this geostrophic assumption that's used to infer what the currents are, it breaks down. And I'll talk about that in a bit later as well. So now I'll talk about some of the methods, other efforts, I guess, to measure surface currents at these finer scales. Again, noting you can't just take a photo of the Earth yet. So this is showing swarms of surface drifters. So these are satellite track drifters deployed in the Gulf of Mexico as part of the GLAD experiment, which was set up after the Deepwater Horizon spill to try and understand the evolution of oil in these complex environments. So what these swarms of drifters do are they allow you to measure the spatial variability of the surface flows, because you have many measurements at the same point in time. Another effort, notable effort, and it's been quite successful around the world, is the high frequency radar network. So how this works is you have these radar antenna. They measure the electromagnetic spectrum, they convert that to a surface wave spectrum, and then they pass that surface wave spectrum through a simple wave current interaction model to infer the surface currents. So this is moving down the scale from measurement to inference. So you're measuring another variable here being the waves, and you're using some simple function to infer the velocity. On the right here, I'm showing, point it back, an example snapshot of that data using the Perth radar network from IMOS. And I've overlaid the currents on the sea surface temperature, so you can see there's this warm core of the Lewin current flowing down to the Perth Canyon, and this eddy shedding off, and the radar captures part of that, but it's limited by how far offshore. And just noting that it's capturing processes at scales less than 100 kilometres. The other way people try and measure surface currents at finer scales is using ships, and like I said earlier, you have to move fast to keep up with some of these processes. So these are some preliminary results from Jianping Peng, who's a new postdoc here at UWA, and he's looked at some data from IMOS and AIMS. So what you're seeing here is a 50-kilometre region of ocean around one of the IMOS moorings, and overlaid sea surface temperature. So you're seeing this front across here, and AIMS drove in this box, so it's 10-kilometre by 10-kilometre box roughly around this around the mooring that also happened to coincide with this front, and starting to see some of the finer variations in the surface currents even as you move across this front. And this data coincided with ocean glider data, so that gave a picture of what's happening beneath the surface in terms of the tracer field as well. So what you see as the glider moves across the front, so going from east to west, is that this sort of layer here, this thermocline, sort of shoals towards the surface as you move across the front. And this all has velocity structure associated with it as well. So the other way people measure surface currents, the spatial variability, and probably the most expensive way is to put out arrays of moorings and current profilers. So these are two examples. One in the North Atlantic where they put out nine moorings separated by about, I think this is about 13 kilometres here, a few kilometres here, and they put them out for a year to measure spatial variability in submesoscale currents. And another local effort from our group where we put out 3 moorings, which was still quite an effort. And these moorings were separated by 600 metres, and they were measuring spatial variability in internal nonlinear internal gravity waves. So all these methods for measuring surface currents are expensive. They require considerable planning, and probably notably, all that planning only gives a short-lived record. So it's really for research, not operational purposes. So now I'll go into ocean models and how we go about modeling the processes down to these scales, and how we use the models to understand how to better collect measurements, and also some of the limitations of the model. So being Thursday before a long weekend, I won't write the equations out. I'll just keep these this form here. So most ocean models are solving the full nonlinear, all the nonlinear terms in horizontal momentum. Some resolve the vertical momentum equation, so that's the second equation you need to solve. And then there's other equations that link conservation of mass, the evolution of traces like temperature and salinity, and an equation of state that links the traces back to fluid density. a few notes on this that, so in terms of the vertical momentum equation, usually drop all the terms and just keep these two, and that's the so-called hydrostatic approximation. This breaks down at finer scales. These terms on the right here, the turbulent shear stresses, and there's also turbulent terms in the tracer equation. They are heavily parameterized, and sometimes poorly as well. So that's a major cause of uncertainty in these models. The other thing is you need initial and boundary conditions of all the variables to be specified, and that's two very large space-time vectors, which also creates uncertainty in your model. And the last thing is that the equations are discretized onto a grid and solved numerically, and that also creates uncertainty. So now I'll just step you through different classes of model and highlight the differences in what they actually resolve. So the first are the global models, and these are operational models. So these are used for actually forecasting what the ocean currents are doing into the future. This is what I'm showing on the left here are surface currents from the Blue Link model, and this has a resolution of 10 kilometres. And this inset here is showing 100 by 100 kilometre box off the Northwest Cape, and so you're seeing what kind of features you're resolving sub 100 kilometre length scale. On the right is I'm showing the sea surface height gradient, and noting, and I'll show this for a few other models as well. The reason I'm showing that is because the sea surface height is actually measurable space, not the current speed. And just noting that at least at the larger scales, that the color here is proportional to the color over here. That's the global scale models. And then moving into regional scale models. So now I'm showing a regional model over Northwest Shelf and the Indo-Australian Basin, showing this free surface height gradient scalar again. And there's two key differences to this model. One, it's higher resolution, so it's 2.5 kilometres. The other thing is I've turned on the tides, so all these waves you can see are the internal gravity wave signature on the free surface height. And then as you move to the coast, you can also see the sloping free surface caused by the surface tides as well. And then here I'm moving into a shelf scale model. So this is a nested model over this region of the Northwest Shelf, the Browse Basin region. So this has a resolution of 500 meters, and yeah, you can see some of the finer scale internal gravity waves that it resolves, and also noting that both these models use the hydrostatic approximation, so the simplified form of the vertical momentum equation. So moving down into models that actually resolve the nonlinear internal waves and the submesoscale eddies. So on the right here, showing a zoom in of a model that has a horizontal scale of 125 meters, and then zooming in to this is a 200 by 200 kilometer box, but you can start seeing these nonlinear internal wave packets in the free surface scalar, or the free surface gradient scalar. So this model is what's called a non-hydrostatic model. So the difference is the vertical momentum equation. To resolve the processes at these scales properly, you need to include all these extra terms in the vertical momentum equation, and that means it's much more expensive to run, basically. And then, so last I'll show this, this plot on the right is going back to from this free surface height gradient, where it's dominated by these lines of nonlinear tonal waves, and then showing what the actual speed, the surface current speed's doing over 100 by 100 kilometre box. So I'll play that. So you can see it's a lot more complicated, noting this is different time periods to this other model. But you do see these eddies being shed off from topography, and they're interacting with these packets of nonlinear waves coming through, and also this sort of pulsing green, grey or whatever it is, beige, is due to the large-scale surface tides and the internal tides that have length scales of 50 to 100 kilometres. So we can't actually see this from space. So what the models do is give us a picture of what we should be looking for in terms of what the surface currents look like. But then I'll go back to the limitations of these models. So I'll restate them, that these turbulent stresses are parameterized. The initial and boundary conditions all must be specified, and they're usually specified from other models, not directly from observations, because we don't have enough observations to properly specify them. And the equations are discretized and solved numerically. And so that means you have a finite size to your grid, so you're only able to resolve features down to a certain length scale. And so I've just included this image from Maddie Rosevere, also in our group at UWA, and she's doing so-called large eddy simulations where you're resolving down to the finest three-dimensional turbulence length scales. And so her model, her ocean model, has a size of 12 metres by 6 metres by 6 metres. And that's all you're able to model, I guess, if you want to resolve everything. Everything else needs parameterizing. So, yeah, I guess the point I wanted to make is that you need to take observations of the surface currents to properly constrain and or validate models resolving these scales of interest, so 1 to 1. So now I'll run through quite quickly some of the efforts within our group to measure these scales. So there's three main projects that are underway. The first is a discovery project where we're looking at data from some of these new satellites. So the SWAT satellite, which I'll talk about soon, and the new Himawari 8, relatively new Himawari 8 geostationary satellite, and trying to infer what the currents are at scales of 10 to 100 kilometres from that data. The second project that's just been received funding is this linkage project with RPS as an industry partner, and that's using satellite imagery and aerial imagery for a camera system, which is to be developed. And that's about inferring surface currents using that imagery of surface waves. I'll show you examples of that. And then the last major project which ties everything together and provides more funding to collect observations. It's TIDE, and the real goal of that is to build prediction systems, and to do that we need these finer scale observations. So just giving a brief overview of what SWOT is, or Surface Water Ocean Topography Satellite. So the satellite altimetry examples I showed before just measure a single track of the sea surface height. What SWOT will do is measure swaths, like two-dimensional swaths of the sea surface height. And so you'll get an across track measure of that tracer, or that scalar. And so that's never been measured, that two-dimensional picture of the sea surface height. And it'll give a better picture basically of some of the eddies and internal waves that are going on, or at least the sea surface expression of those. Some of the details, it's not in space yet. It's launched at the end of this year, and at the start of next year or mid next year, there'll be this calibration phase where the satellite flies over selected regions once per day, and during that time you'll be able to get higher frequency data of this sea surface height variable. Normally it flies over every 21 days, so pretty much lower frequency. So there's a few challenges with how you actually go from this SWOT data to currents. The first is the geostrophic balance that's used for the traditional satellites breaks down at these scales, so you can no longer do this to get the surface currents. In the nominal orbit, the satellite repeats will only be every 21 days. And the problem with that is the processes at scales of 10 to 100 kilometres evolve much more quickly. So you need to basically build models that can interpolate between measurements. And the third thing is, because you're getting just this snapshot once every 21 days, internal gravity waves and submesoscale eddies have similar length scales, and because you get this snapshot, it's difficult to separate them from one another. So that's a big challenge as well. So, I mean, what we proposed is to do an intensive field campaign during the so-called calibration phase of the mission. So this is one of the tracks where it flies over the Browse Basin region. So we're planning to focus on part of this region. So zooming in here, and what we're planning to do is putting out moorings and doing ship-based data, like that ship-based ADCP data I showed earlier, and basically to try and use that in situ data to help understand the temporal evolution of some of the processes that are poorly sampled in time by the satellite. So in particular, these internal gravity waves. So in terms of internal waves and eddy disentanglement, so if you can separate the two, internal waves and eddies, from the satellite signal, you can actually use simplified models to infer what the currents are. So the separation is one of the challenges of the data. And just to show you, so this is that model of the sea surface height gradient, what it would look like if you could measure everywhere for all time. And this is what, if you filter out the internal gravity waves from that signal, this is what you get left with. So it's those slow moving rotational eddies, which are of interest as well. So the other approach and the last approach for trying to infer the currents from this SWOT data is to combine the sea surface height with another tracer, so sea surface temperature. So it happens that there's this Himawari 8 geostationary satellite over Australia, and it measures temperature every 10 minutes at 2 kilometre resolution. So the goal is to use this additional data to constrain some of these inverse models going from SSH, sea surface height, to currents. And last note that it can also be used to, you can directly invert this using tracer evolution equation, although it's unconstrained. So the second project is this linkage project, and it's around extracting surface currents from imagery of surface waves. And so the basic principle here is if you have a time-lagged sequence of the ocean surface with high enough resolution, so this is a 2.5 kilometre box here, and if you have time lags, so of a second or two between these images, you can do a Fourier transform on this signal to get the surface waves, and then you can look for the phase shift in these surface waves. So this is what I'm doing here. So I'm plotting the wave numbers in the horizontal plane, and look at the phase shift. And what you can do is you can look at the measured phase shift and take the difference between the theoretical phase shift with no currents, and you can invert out what the currents are over this 2.5 kilometre squared region. So sounds good, and it works. So this is an example where we grabbed 2 tiles around Rottnest, or offshore of Perth, and so this is 200 kilometres across here. And so that example before is we get one velocity estimate for one of these vectors here. So this red box is this one. But yeah, so you can start seeing the spatial variability in the currents over these 1 to 200 kilometre length scales. So again, this is sea surface temperature in the background. You can see this eddy that I showed earlier, and you're starting to pick up some of that velocity structure in that eddy. For comparison, this is the HF radar estimates, and noting that its range is limited to the coastline, so not able to pick. So in terms of this project, there's a few main goals. First is to go back through the Sentinel-2 archive and actually do some validation with historical in situ observations to try and refine some of the inversion methods for getting the currents. The second and important aim is to develop an integrated camera and navigation system that can be installed in small aircraft and used to fly out on demand and collect higher resolution imagery than you'd otherwise get from the satellite. So high resolution means potentially collect currents at finer length scales and what we do with the satellite. And third, we're looking at developing new algorithms for extracting the currents at these scales, in particular looking at how we can get not just a single estimate of the current, but also the vertical shear. And then, so lastly, all this ties into the TIDE, so the Transforming Energy Infrastructure through Digital Engineering Research Hub. And this, yeah, I'm sure you've heard a lot about this, but there's the oceanography focus of TIDE is around prediction, and in particular prediction of the surface currents due to these smaller scale processes, so nonlinear internal waves, submesoscale eddies. And the approach is to combine these physical models, which I've been talking about, and some new data science techniques, which I won't go into at all today. And so the outputs, the goal is to take the outputs from those two other projects, so the SWAT, Inwari 8, and the Sentinel-2 type currents, and feed them into these new hybrid approaches, so combining physics with data science methods. And yeah, so yeah, the ultimate goal in TIDE is to use these predictions to make informed decisions around operations and or design in the offshore environment. So I'll finish there. Some key take homes for the long weekend are: 1, ocean variability at 1 to 100 kilometres is dominated by these submesoscale eddies and internal gravity waves. 2, ocean currents are hard to directly measure at these scales, and the difficulty is capturing both the spatial and temporal variability with any platform, be it satellite or vessel. So the currents really must be inferred using these other ocean variables like sea surface height or surface waves. And I guess the other thing to note is that these simple balances, or these simple models, tend to break down at smaller scales. So that means inverting more complicated nonlinear models using different variables. And so really, to get the job done, you need to combine remote sensing with in situ data and inversion/data science methods to infer what the currents are doing at these smaller scales. So I'll leave it there and I guess open up to questions. So reading the first one, Ashvath. Okay, so this is, okay, proof. Yeah, I guess that was a loose use of the word proof. So the question's really about how do the fine scale processes affect the large scale processes, and what is the proof? So I guess the proof has been through models, and basically showing that if you either resolve or parameterize some of the finer scale processes, then they have an effect on the large scale circulation. I guess a good example of that is people have shown that if you parameterize the effects of mixing by internal gravity waves in climate models, the global circulation is altered. Nick has asked, can the SWAT be tasked with covering an area of specific interest, and who controls where and when it SWATs? And so the answer to that is no, Nick. It has a predefined orbit, so it will just measure the sea surface height when it's there, same as the other altimeters, really. So the idea is to get the repeated cycle consistently. Yeah, it's so Nick's asked what part of the Earth's ocean does it cover? Yeah, it's the whole globe, including the poles. So I will note that because it's doing this interleaving orbit, there will be regions that are sampled every 10 days or every 5 days. So I guess they'll be of interest to people as well. Vadim has asked, what can we learn from the body experiment? So yeah, I didn't talk about the body. So this is a browse ocean dynamics experiment that was funded through the Shell Chair, I believe, where they've been deploying drifters around Prelude, and sometimes they've done it in clusters. Yeah, it's a good question, Vadim. I think some analysis can be done when there were clusters of drifters together. So you can calculate things like spatial structure functions or spatial decorrelation length scales from that data, which can then inform some of these data science methods or the data assimilation methods as well. Any more? Give it 15 more seconds and then it's long weekend time. Yeah, it's yeah, there will be issues with computing SSH gradient from SWAT, given the noise. True. All right. Unless there's any more questions, unmute yourself now or call it a day. All right. Well, thanks everyone again, and enjoy your Easter break. Bye.